cover today mainly has to do with polarization of light. I'm going to go through this very quickly since we have very little time left. So who knows what light is? It's a wave and a particle. Excellent. Okay. So historically, there has been a big debate as to whether or not light was a particle or a wave. Well, for hundreds and hundreds of years, people that have been thinking about light have wondered whether it was a particle or a wave. Since we're studying waves, we've been studying the aspects of light that lead us to believe that it is a wave. What are some of the things that light does that tells us that it's a wave? Okay, which means it will then refract. Excellent. So refraction, interference. It reflects, but remember that reflection is not inherent to only waves. Reflection, a particle would do the same thing, right? So even though light reflects, that doesn't tell us whether it's a particle or wave. But refraction, superposition, refraction, what were we saying? Diffraction, great. Those are the things that tell us that light is a wave. We talked about Thomas Young doing his experiment with the two openings in the early 1800s to prove that light was a wave. Okay, that was because the light was diffracting. If it were not a wave, if it were a particle, it would not have diffracted through those openings. The fact that light refracts, and we can do this penny in the cup experiment. If we have some time at the end of class, we'll try that. But the fact that it refracts tells us that it's a wave, because particles don't refract. Waves do. Let's see. Polarization is a quality of light that can only happen if light is a wave. And we'll talk about polarization today and what that means. And finally, thin film interference is another thing that we've observed. You ever notice on, let's say, if you have water with a little bit of oil on top of it, you see rainbows? You ever notice that? Or like soap bubbles, you see rainbows? Okay? That's thin film interference. That's superposition interference. And again, that is a wave prop. Okay, so what is waving? We talk about light being a wave. What is waving? Well, we call it electromagnetic radiation. And what is waving is an electric field and a magnetic field. So there's not actually a material that's waving, and this is why light or electromagnetic waves can travel through a vacuum. They are not mechanical because they don't require a medium to oscillate, because the thing that is oscillating is an electric field and a magnetic field. And you guys remember with our right-hand rules in electromagnetism, they're intimately related and they affect one another. So in this picture, this is kind of the best visualization I could find of it. Imagine this light ray traveling from left to right. The thing that is oscillating is the electric field, which is this red wave. And as it gets bigger and as it changes, it generates a magnetic field, which is the blue wave. And they oscillate perpendicular to one another, and they both are oscillating perpendicular to the direction of wave travel. So what kind of a wave would it be? Transverse wave, because the oscillations of the fields are perpendicular to the direction of motion. With me so far? Good. So for all intents and purposes on this discussion, you guys, we're going to forget about the magnetic field for a little while. When we talk about polarization, we generally just kind of think of one of these fields. But remember that there's actually two of them. But for simplicity, we'll just think about the electric field vibrating in a certain direction. And the idea with polarization is this. If I have a light ray going into the board, so this little circle is my light ray going into the board. You with me? Remember, the electric field and the magnetic field are oscillating perpendicular to that direction. But I'm going to forget about the magnetic field and just deal with the electric field for a second. So I could have an electric field that is oscillating like this, right? That's perpendicular to my ray because it's a transverse wave. But I could also have an electric field oscillating like this. Yes? Or like this. Or like this. Or really, I could draw an infinite number of directions in which my electric field would be oscillating, and it would still be perpendicular to my light ray, okay? Most sources of light, a light bulb, the sun, stuff like that, when they create light, this is what's happening. You've got electric fields that are oscillating in all directions perpendicular to the direction of travel. And we would say that that light is not polarized or unpolarized. But if I do something to it, if I do something to the light, so I get rid of many of these directions of oscillation, and all I have left is one, now it's just oscillating up and down as my light ray travels into the board, I would say that that light beam is plane polarized. It's polarized in one plane. It's only oscillating in one plane. You with me? There's ways we can do this, but right now I'm just giving you the terminology. Does that make sense, the difference between unpolarized and polarized? Cool. Now here's a cool thing about polarization. If I have a wave that is polarized, hang on one second, Sam. If I have a wave that is polarized, like this wave on this string, notice in picture A that I've got this string and I'm creating a transverse wave and it's vertically plane polarized. It's not isolating in any other way other than vertically. If I take that wave and I send it through a vertical opening, It'll go through no problem. That's cool. I can do that. But if I take a horizontally plane polarized wave and try to stick it through a vertical opening, notice that nothing comes out the other side. And we can do this with light. When I get light that's polarized in a certain direction and I try to pass it through an opening that's oriented a different direction, it won't go through. Okay? It looks like darkness. Yes. So here is kind of how polarization works. And we have filters. We have what we call polarized filters, things that will polarize light. And I think an easy way to imagine a polarized filter, I always imagine them like a jail cell. You got these vertical bars, right? So notice if I have light traveling along, and this is regular unpolarized light, it's oscillating in an infinite number of directions perpendicular to the way it's traveling. They've only drawn 2, but you can imagine there's many more, right? And it's traveling along, and it hits this filter, what we call a polarizer. Because what happens is it only allows one plane of oscillation to get through, and it blocks out all the others. And now I'd say my light is plane polarized. And in this case, it's vertically polarized because my polarizer was oriented vertically. If I take a second polarizer, which we would call an analyzer, and rotate it so it is perpendicular to that, notice that the light is vertical, the axis here is horizontal, nothing gets through. Kind of. Sunglasses do this. Sunglasses are like your polarizer because there's only one of them there. And so what they do is you've got light coming along, and they only allow some of it through. And actually, they allow half of it through. 50% of it gets through. Because why do you wear sunglasses? To make it darker, right? To get rid of some of the light. The other thing that polarized glasses do is they reduce glare. And this is why fishermen love them. And we'll talk about why in a second. Okay? Here's your first equation with polarization. It's a relatively simple equation. Here's what it's called Malice's law. And basically, this is an equation that allows me to calculate the intensity of the light that gets through a polarized filter. Okay? And it's pretty simple. The intensity that gets through is equal to the intensity that hits it times the cosine squared of the angle between the polarization of the light that's coming in and the axis of the filter. Okay? Are you guys familiar with this, that way of writing it? What we're saying is it's cosine of the angle, and that answer is squared. It's not the angle squared, it's the answer squared. You see what I'm saying? So it's like cosine of 30 degrees. It's degrees. This one's degrees. And I wanted to talk to you about that whole radian thing before because I went back and researched it. Because remember you were asking me all that? So talk to me about that. Let's go. Okay. This is in degrees. Okay. Does that make sense? Now here's a weird thing. If this incoming light here, if this incoming light is not polarized, right? Imagine if it's not polarized, I can break every single one down into horizontal components and vertical components, right? Because remember vectors, I can break everything down into horizontal and vertical. So essentially what's going to happen is it's going to block out all of one and allow all of the other through. And the net result is if unpolarized light goes through a polarized filter, 50% of the light gets through. 50% gets blocked, 50% gets through. So that's always the case. Okay. But if you had time to let's look at this practice problem real quick and then we'll just move on, okay? So I've got unpolarized or vertically polarized light that hits a filter at 30 degrees. Can we do that real quick? What percentage will get through? Vertically polarized light. No, this is already polarized light, and it's hitting a filter at 30 degrees to the vertical. How would I figure out what's the deal here? It would end up being 9/16. Okay? Of the initial intensity. All right? Cool. Let's talk about the Brewster angle. Brewster's law. A lot of you are going to go, oh, cool, Brewster, dude. All right, so here's one of the reasons why we wear polarized sunglasses is because when light reflects off of a non-metallic surface, when light bounces off of a non-metallic surface, it becomes polarized just by reflection. And it will mostly be polarized in the plane of the surface that it bounces off of. So I've got a light ray coming in that's unpolarized, it's oscillating in all different directions, it bounces off of this surface. It will mostly be polarized in and out of the board here, parallel to the plane of the surface. But it'll also have a little bit more of oscillations in the other plane. There is a certain angle. There's a certain angle, which I'm going to call the Brewster's angle. When it comes in, when the light that bounces off the surface is completely 100% polarized in the plane of the surface that it bounced off of. Okay, that angle that it happens is known as Brewster's angle. It just so happens that the angle that it does this is when the refracted ray is perpendicular to the reflected ray, okay? When the refracted ray is at 90 degrees to the reflected ray, that is when this reflected ray will be 100% polarized. The angle at which that happens is known as Brewster's angle, and the math to solve it is relatively simple, which I'll show you here in just one moment. Okay? Okay, it's just to find Brewster's angle. Come on. There we go. You need to know the index of refraction of the material that the light is bouncing off of. And as long as it's coming from air and hitting that material and bouncing off of it, tangent of Brewster's angle equals the index of refraction of that new material. Okay? This is why polarized sunglasses reduce glare. Because if reflected light, that's what we call glare, it's horizontally polarized. If you put on glasses that are vertically polarized, that reflected light doesn't get through. And so when you look at the surface of the water, you can see into the water rather than seeing the glare off the surface. That's why fishermen love polarized glasses. And for you and me, that just reduces glare, which is kind of nice if you're not a fisherman. Okay? What's the Brewster angle for light reflecting off of water? What's the Brewster angle for light reflecting off of water? You have 8 seconds. N equals tangent theta, and N is 1.33. Yeah, which is, excellent, 53 degrees, okay? So light that's reflecting off of water at 53 degrees is perfectly polarized. It's 100% vibrating horizontally. If you've got your polarized glasses that are vertically oriented, none of that light gets to your eyes and you don't see that glare at all, okay? That's what Brewster's angle is. Now, optical activity is the last thing I want to talk about, and then I want to get some specific applications of polarization. The weird thing is there are some materials that if I shine polarized light through them that's already polarized in a certain direction, the plane of polarization will rotate as it goes through that material. And a material that does that is said to be optically active. The first materials that were discovered to do that were certain crystals and certain solutions, like sugar solutions, okay? The amount of rotation depends on the concentration of the solution and also how much of the solution the light goes through. So actually this is a tool that sometimes is used to measure solution concentrations. If someone hands you a beaker of water and says, what's the concentration of the sugar solution? If you know the math, all you have to do is shine polarized light through it and see how much that plane of polarization is rotated, and you can determine the concentration, which is kind of crazy. Some other applications of polarized light are stress analysis. Have you ever noticed with polarized glasses, sometimes you look at it through a window or through a piece of glass and you see like weird rainbows and lines and stuff like that? That's because the glass has been stressed. And if glass or plastic gets stressed, it becomes optically active, and it will rotate the plane of polarization. You can actually see that with polarized glasses, okay? By like bending it or pushing on it or breaking it or drilling something through it, that stresses it, okay?
Is that why when you look at like a radio with the glasses on,
We'll talk about that in a second. We talked about how polarization can reduce glare because glare is reflected light, which becomes polarized. Great. We can measure concentrations of solutions. LCDs are a very common application, and this is why you can't see the radios, because it's an LCD screen. LCDs are a very common application of polarization, and we use them all the time. Most screens that you look at on your calculator, on your watch, on the radio, little screen that tells you something, those are LCD screens, and now we're actually making entire televisions and computer monitors that are LCD as well. What does LCD stand for? Liquid Crystal Display. Liquid Crystal Display, okay? And it's really an ingenious thing, and I want to show you how it works because I think it's just cool. Each individual dot on your calculator screen is what we call a pixel, or a picture element, and pixel is short for that. What do you see on your calculator screen? What do you see about the pixels? What can they be? There's They can become numbers and letters, but each pixel can be black or white, black or light, on or off. But you can either see that they're light or they're black, correct? Here's what's going on. You've got light coming from the room. You've got light coming from the room, and it hits I'm going to look at one individual LCD pixel right now, okay? It goes through a piece of glass, and that piece of glass is designed to polarize the light, okay? So the light goes through, and it's now polarized. And let's say it's polarized left to right once it goes through this glass, okay? Then it goes through a little section that has the liquid crystal in it. Here's my liquid crystal. And you can imagine the liquid crystal is optically active. It's like a spiral staircase is how I imagine it. It's these long molecules that are connected in a spiral pattern so that as the light that is polarized left to right, when it goes through, it turns 90 degrees. And so by the bottom, my light is now polarized into and out of the board. You with me so far? Good. Then there's a second piece of glass that's polarized into and out of the board. So that light goes through. And then it hits a mirror back here, reflects off, comes back, and the light comes back out, and that particular pixel is light. I can see it as a light-colored pixel. I need to be able to make it dark, and here's how I make it dark. It turns out there's some electrodes in here, okay? There's also electrodes in here, positive and negative terminal. When I pass electricity through my liquid crystals, when I put a potential difference across them, instead of being like a spiral staircase, they go bing, and they line up parallel. They line up with the electric field that I create. And so suddenly, my light that comes through that's polarized left to right doesn't rotate 90 degrees. It stays left to right, hits the second filter, and doesn't go through. And that pixel has then become dark. Okay? And then you have a sort of a computer chip in there that tells which pixels to be dark, which pixels to be light, and you see that as letters and numbers and things. Okay? Now, that's a basic black and white LCD screen. Notice that your calculator screen is a pretty basic screen, and if you were to do it in a dark room, you wouldn't be able to see what it says because it requires light from the outside to come in. Some of you have LCD monitors, like on most laptop computers or on your TV at home, which show color and also are glowing in and of themselves. They're slightly different, but the idea is the same. Instead, here you are out here watching TV, and instead, they have the same setup. They have glass filters. They have your liquid crystals in here. They have another glass polarized filter, but instead of a mirror, they have a light source back here. Okay, so they're backlit. The light goes through, gets polarized, same idea, and then the only other difference is each pixel has a filter on it. It's either red, green, or blue. And then you can control how much of the red or the green or the blue light pixel lights up, and by combining red and green and blue light, you make all the colors of the rainbow, and you do it really fast. So here's kind of a picture of it. Okay, here's your basic black and white one, right? Notice the light comes through. Okay, it gets polarized here. Here's the crystals that rotate at 90 degrees. It gets through the second filter, bounces off, comes back out, and that particular thing looks like a light pixel. When I put electricity across my electrodes, the crystals line up parallel to one another so that the polarized light does not rotate, it does not get through the second filter, and then that pixel becomes dark. Pretty simple stuff, okay? Now, and then here's the colorized version. You have different pixels that are red, green, or blue. You can control how much light gets through each one, and therefore control the intensity, and when you mix those three colors, you can create every other color. Okay? All right. Wavelengths of light, that's color. All right, Roy Biv. Wavelengths of light are really small, you guys. We're talking hundreds of billionths of a meter long. Okay? Ultraviolet and infrared, we want to talk about. Speed of light's really fast. Remember that Galileo or Newton tried to measure it. Ole Romer was the first one to actually measure it using Io, which was a moon of Jupiter. And then the great American physicist Michelson was able to measure it very, very accurately. We know it's really fast. 3 times 10 to the 8th meters per second, 7.5 times around the world every second. Can't answer questions right now. Electromagnetic spectrum. Okay, we got other kinds. Know that you understand that we have other kinds of electromagnetic radiation, and this is kind of the electromagnetic spectrum. So I want you to see this for a second. Notice that visible light is a very small piece of a much larger spectrum of electromagnetic waves. And when the waves get longer, we call them radio waves. Okay, those are the longest ones. And then they get a little bit shorter, we call them microwaves. And then a little bit shorter yet, we call them infrared. And then visible light, notice red is long and blue is short, so infrared is longer than red. When you get shorter than violet, we call it, hey, that's cool. That's like ultraviolet, man. It's even smaller, okay? Ultraviolet gives you sunburn and also causes skin cancer and damages DNA, so it's dangerous for animals that lay eggs that don't have protective shells. X-rays are even smaller and more damaging yet, and then you have gamma rays. Now, we are bottom feeders. We're like lobsters. We live on the bottom of this thing we call the atmosphere. And the cool thing about our atmosphere is that it protects us from all that radiation in space, because out in space you get all that kind of radiation from different sources. And notice that the gamma rays, this red line shows you what gets through the atmosphere. Where there's no red line, it gets through the atmosphere. And notice visible light does get through, which is kind of nice because we can see, right? But gamma rays don't get through. X-rays don't get through. UV doesn't get through, though we tried to let it get through by destroying the ozone layer, but we're doing a better job of that now. Okay, infrared and microwave don't get through. But look, there's a band of radio waves that do get through. So, as an astronomer, I know you guys want to go, but hang on, let me finish. As an astronomer, you build telescopes. And if you live on Earth, what kind of telescopes are you going to build? Visible light telescopes and radio. Those are the two kinds of waves that we can see from space that get through our atmosphere. And if you notice that most ground-based telescopes are either visible light telescopes that are just looking at visible light, or we build giant radio telescopes like you saw in the movie Contact. Oh, yeah. Well, not see them, but we can collect them and analyze them. Yes, and then you can learn things that way. We have since, they don't look like anything to us because we don't detect them with our eyes. Those are huge dishes. Like, did you see the movie Contact with Jodie Foster? Because radio waves are so big, they require enormous. They look like a telescope. They look like like the satellite dish for satellite radio when you're home, but much, much larger. Okay. Arecibo, like James Bond, that big crater that they made a telescope out of. That's a radio telescope. Okay. Yeah. Oh, those are just heat waves and stuff that you see in the air. Okay. We have made, you guys, we have made X-ray telescopes and we have made gamma ray telescopes. Where are they located? In space, okay? We have learned so much by observing the universe in other wavelengths. If you have a chance, if we had time today, I'd show you right now, you should go to the Chandra X-ray Observatory website, Google it, and you see some awesome images where we've got these images that we took pictures of, like nebula in the visible light using the Hubble telescope, and then we overlay what we learned in the X-rays using the Chandra Observatory, and you can learn so much more that way by looking at other wavelengths of light.